So when we talk about metathesis reactions and double replacement reactions, we find that two ions exchange places. For example, if you have AX and BY as compounds, where we have A would be the cation and the anion would be the X, and then over here you'd have a plus and a minus, like that. Well, what you would want to do is take the A and hook it up with Y and the B and hook it up with X. So you put little brackets under it like that, and so AX plus BY goes to AY plus BX, like that. Now, it's not just swapping ions, it's identifying what is the driving force of this process. One of these substances over here will pull the reaction to completion, and in doing so, it's called a driving force. So one of the product compounds is a driving force in that it leaves the system. What does that mean? It either precipitates out as a solid and everything else stays in solution, or it goes into a compound form that is a weak acid or a weak base, or it leaves the system as a gas decomposition. So driving forces compounds are of three forms: an insoluble precipitant or salt, a weak acid or weak base, or a gas decomposition product. And if you have one of those, you'll need it right now. Okay, like I said, it's divided into three classes or categories of compounds that you'll find always on the product side of the reaction. So a driving force is on the product side of the reaction if it has a driving force. Now, you'll notice the first two tables here are solid precipitants. And so in a metathesis reaction, you're looking for a compound on the product side that will precipitate from solution or has a very, very low solubility factor. And if it's not a strong acid, then it can be a weak acid. So weak acids are driving forces of some reactions. And then down here it gives you some examples of the decompositions. Over here on the left, bottom left, you'll see the compounds that will break down from other compounds, weak acids primarily, and give you a gas, and that will bubble out of the solution. And the object of, say, a driving force is to prevent the reaction from going back to the reactant side. So it pulls the reaction to completion and makes everything convert to whatever products they are predicted by that reaction process. So the object here is to define the reactions and some examples and show you how to walk through several in examples. Y'all have that?
Yes, sir.
Okay. If you do not, I can make some later, or you can jot these down as you wish. And that so. But this is a lab. Now I want you to complete this, and I will make some more of these. And when you complete it, you staple it together, put your name on it, and chair number, and turn it in. Now you can finish it by next class. because I want everybody, and I'll work through some specifics on this and show you what needs to be done. But when you turn it in, it'll be graded as a lab, and this is kind of a together workshop. Okay, so we're going to be working on this one and predicting the outcome of it. A little easier to. Now, to begin with, you need to identify the cations and anions in the each compound. When you're looking at a salt or a complex structure like this contains a polyion, read it from left to right and mentally petition the first metal in the compound from the remaining part of the formula. The first metal in here is always the cation. And then the remaining portion of the compound is the anion. Same way over here with the sodium hydroxide. You petition this here, and this one is, of course, your cation. And then the remaining portion of the compound is the anion, as shown here. Everybody good on that? So from the first metal only, that's your cation. Now the only one that differs from this is the NH4, the ammonium ion. But all of the other examples and compounds and reactions that you'll do will have a metal and then rest of the compound. And the rest of the compound will always be the anion after that first metal. Regardless, now the polyions may have a metal in it, like dichromate, Cr2O7. You may have sodium dichromate, Na and then Cr. But split off the sodium, then the chromate ion appeared. Now, in this, what you want to do is you want to connect the cation from compound 1 with the anion of compound 2. And then the anion of compound 1 with the cation of compound 2. And write the formulas with the cation written first, followed by the anion. So we would have sodium chloride followed by iron hydroxide. Now, what I did is wrote the substances together without taking into account the oxidation states at this point. Then, once you put them together and make the exchange, then apply the oxidation states and sum of charges equals 0. So, sodium's always a +1, chloride's always a -1, so this is a correct formula. Over here, we find hydroxide ion is always a -1, and iron, well, we know it's going to be a +2 because the initial problem says iron 2. And so iron 2 has an oxidation state of +2. Everybody good on that? Okay. Then you look at this and you've got to balance the charge. So sum of charges must equal 0. So I have to have 2 of those, and so that gives me a net -2 overall. So those are the correct ratios of compounds in the formula. Now, which of these two would represent the driving force? It has to be an insoluble, not a soluble, insoluble salt or compound, or a weak electrolyte, weak acid or weak base, or a gas decomposition product. Now, you determine that from this table. This will be attached to the big exam. Okay, and I'll attach it to your quiz. So it really helps you, but you have to know how to interpret it. So what can we say about NaCl? All right, if you look at these two tables here, okay, you have solubility of ionic compounds, soluble substances. See where the word soluble means, yeah, that's not a driving force. Hear me? Not when it says soluble, it's not a driving force. Not a driving. And down here, insolubles are driving forces. They'll be precipitating out of the systems. Now, there are some exceptions to whatever's over here. Like if it's soluble compounds, class of compounds, there are exceptions which are driving forces. These salts are insoluble and therefore they are driving forces because they are the exceptions to what is soluble. Insolubles, and then there are exceptions. These are not driving forces at the second table on the right side. So you have to find something that is insoluble. So we look at the compounds. This says this is a halide or halogen. So we look on this sheet and we find halogens or halides. Well, there are your halides right there. What it says. Halides are group 7, if you didn't remember that. Fluoride, chloride, bromide, and iodide, those 4. All halides, whatever they are, if it has a halogen on the end of in the anionic position, okay, is a halide. And all of them are soluble in the whole wide world and universe and are not driving forces. Except if that metal is one of these 3. If mercury halide, mercury chloride, mercury bromide, mercury iodide, or lead, silver, silver chloride, silver bromide, silver iodide, silver fluoride, or you might see a lead chloride, bromide, or iodide. Yeah, those would be driving forces. So when we look at our compound now, is that a silver, lead, or mercury? No. So this is not a driving force. It remains soluble. That's what I'm trying to teach you here. See the point? How to use the table. All right. How do you remember them, though? I call them the happy halides. HAP. Happy. Mercury, silver, and lead are the 3 only halides that will fall out of solution. Okay? When you decide on that compound that it's a soluble and not a driving force, listen to me. It does not mean the other one is a driving force. That's not true. And in this case, yeah, because I'll show you that. But I'll throw in curveballs to you in an exam where both of them are soluble. And I'll show you an example before we quit. And it doesn't have a driving, and the response to that is no reaction occurs, is what you'll say in that. Okay, see what I'm getting at? Okay, so the idea is you find the solid, liquid, or soluble, find the precipitant, the acid or base, and or the gas, and that's a driving force. But sometimes they don't have them. They don't fit this. I'll show you. It is pretty straight once you see it. Now, is this a driving force? So we look over here in this collection over here. Here we find hydroxides here. So we want to ask ourselves, is this insoluble? Yeah, it's a class of compound that is insoluble. And therefore, yeah, that's a driving force if it is insoluble. Now, is it a member of the exceptions over here? Okay, let's see, group 1A. Well, let's look on the periodic chart. You'll have that attached to the, is it lithium? No, it's not lithium. It's not sodium or potassium, rubidium, or cesium. So, okay, so it's not a member of that collection right there, so it's insoluble. If you had a group 1 metal attached, you couldn't call it a driving force because it would all group 1 metals are soluble and not driving forces. How about ammonium? Well, that doesn't look like ammonium, that looks like iron. Okay, the ammonium hydroxides are all soluble, but they fall under a different category. You'll see it's a gas decomp. And barium and strontium, well, this doesn't look like anything like barium or strontium. That's iron too. So this is the driving force. And the way you identify it, you just put an S out here in the end for solid, and you put an AQ on this one because it stays in solution. Now, everybody kind of follow me on at least the precipitate? Okay. Now, this is referred to as the molecular equation. And so in your handout, when you fill out this right here, you want to write this equation in that blank. That's what I want you to do. But you have two other equations. One is an ionic equation, and one is a net ionic equation. Now, the rules on this, on writing an ionic and net ionic equation is if it's a weak electrolyte, that is a weak acid or a weak base, you do not write it in a ionic form. If it's a driving force, you don't write it in ionic form. Now, what does that mean? That means showing the compound in cation and anion form. That's what it means. So in this one, you don't have a driving force on the left side of this, and neither one of those are weak electrolytes. And so we would write this iron plus 2, and to be absolutely correct, you want to indicate it to be in water, and that'd be your aqueous. And then you have 2 chlorides minus. You have to take the subscript and use it as a coefficient now, aqueous. Continue with the next compound, that would be sodium cation, aqueous, and then your polyion would be written like that. So there are all of the reactants listed in ionic form. We'll do one in a minute that is a weak electrolyte on the reactant side. I'll show you that in a minute. Then proceed to the product side, and since this is not a driving force, you would show it in the ionic form, so it would be a sodium, an aqueous, and a chloride, aqueous. Do not show the driving force in ionic form. So you just write it in the molecular equation form. And put an S out there on the end. So there is your composite or total ionic equation. It shows all the necessary compounds in ionic form. Now, when you look to the substances on the left of the arrow and the substances on the right of the arrow, you find some that are matching. That means sodium and chloride. There it is, chloride. And this has to have a 2 in front of that and a 2 in front of that, and that should be, well, we haven't balanced our equation, have we? I got to have 2 here. Okay. And that's going to give me 2 there, and so that, yeah, sorry. You're supposed to balance the equation. Yeah. Okay, so we have 2 here. So you see on the left and the right of an arrow, you have matching amounts as well as substances. Well, these are spectator ions, and you can remove those like you would cancel out an algebra problem of sorts. The remaining substances are the compounds that undergo reaction, and when you write those down in equation form, it's an ionic equation and it's a net ionic equation. So we have iron in aqueous form, and then we have hydroxide. I need a 2 right there, I forgot that. 2 hydroxides, aqueous, and that will go to your iron hydroxide. Now, this is not a difficult exercise and not difficult to learn, but you do have to apply yourself into these examples as we go through, and I'll give you a couple more that I want to work. Again, this is the molecular equation. This is the ionic equation. and this is the net ionic equation. This is an example of an acid-base reaction. How do I know that that's an acid? It's got that hydrogen hanging out in front of it. Now, there are other formulas that define acids that have the hydrogen in a different place. I'll give you a quick example. There is the acidic hydrogen on the end like this, and this is used frequently in organic chemistry, but you will see me use this form, and if I have to go to something else, I'll be real clear about its notation and who's the ionic component of it. Okay, so you want to start out by predicting the cation-anion exchange. Okay, so that's a hydrogen, and there's your acetate right there. So that's +1, and that's -1. And remember, in all of these, the ionic charge on the reactant side is the same as the ionic charge on the product side. So you don't have to lose that, but you do have to use them in defining the subscripts that you'll need. Here is a minus, and this is, of course, a +1. And so what you want to do is connect the cation from the first compound with the anion, the second one, and then the anion of the first one with the cation, the second one, like that, to produce the product side of your reaction. So this would be a sodium acetate and water. I'm going to write this in a little bit different form. I'm just going to H hooking up with the OH. Now, you have to determine what the subscripts are and balance it. Well, this is still a +1, and this is still a -1, so that's the correct formula. Remember, you go to the first metal, sodium, and mentally isolate that one from everything else. Everything else is the anion. Remember? Then when you talk about water, see the hydrogen comes over and hooks up with the OH. That's why I'm writing it like that, just so you'll see the cation anion thing. So there's your +1 and anion like that. Everybody good? Okay. So now you have to determine which one is a driving force. In acid-base reactions, the driving force is a weak acid or weak base. Okay, such that the hydrogen hooks up with the anion, say for example OH, more strongly than the hydrogen would hook up with the acetate ion. So that's why I'm showing it over here. Well, how do I know? Well, this is honestly a weak acid. Water is a weak acid. How do I know that? How do I know that, guys? I told you earlier, if it ain't a member of the strong six, it's a weak acid. Doesn't matter whether you know it is or not. That ain't an HCl, HBr, HI, HNO3, HClO4, H2SO4. So it is a weak acid, and therefore driving force. Yes? Okay, see what I'm getting at? So you look over here and see, well, what's the driving force? Well, that has an H hanging out in front of it, so that's going to be an acid. Is it a strong acid? No, then it's a driving force. Is that a driving force possible? No, it's a salt. How do I know? It's a metal, and the polyion is the nonmetal. This is a metal-nonmetal combination, which is an ionic compound, salt, same word, so to speak, and therefore it remains ionized. All acetate ions are There's no acetates that are precipitating from solution. Look at your driving force table. Let's see if it has it in here. Acetate salts, all soluble. There you go. So you look at it and you have to know your polyions. That's why I made a big issue out of it. So, this being the driving force, water, now we can write the ionic equation. Now what I told you is if it's a weak acid or a weak base or driving force, do not show it ionized. Well, is this a weak acid? Yeah, we know it's a weak acid because it's not a member of the big six, and we know it's an acid because it has an H hanging out in front of the formula. I'll give you that. So if it's a weak acid, you do not show it in ionic form. So when you write your ionic equation, you start with this. And you'll write it in that form. Well, then you go over here. Now, I've told you what the strong acids are. Strong acids are, the strong six. But I haven't told you what the strong bases are. The strong bases are group 1A bases. That is your lithium, sodium, potassium, rubidium, cesium, francium, with an OH hanging on it. Any one of those is a strong base. That means it ionizes 100% across this structure right there. And so if it does ionize 100%, yes, you show it in ionic form. Like that. So you have to show that one in ionic form. Then you go over here, all salts. Here's a rule you need to remember, and I'll say it many times in the future. All salts ionize 100%, but not all salts have the same solubility. Some salts have very, very low solubilities as shown on this driving force sheet. Those that are all many hydroxides, phosphates, carbonates, and sulfides have a very, very low solubilities, except for the minor exceptions is what they're showing. So when you are talking about a group 1 acetate, it's not one of the low solubility compounds. It's a group 1 acetate ionized 100%. They're totally soluble. So you have to show that as a salt, they always ionize 100%. So if you see a metal, non-metal, including the polyion, show it ionized. Metal, polyion, ionize it. Now, the driving force, is that a weak acid? Yes, it is the driving force, and you do not show it in ionic form. This is your ionic equation. It has only one spectator ion, so you can cancel that, and the net of this is everything except the sodium, and so you have HC2H3O2 aqueous plus the hydroxide aqueous going to the acetate ion C2H3O2 minus aqueous plus water. Right there. So if you had, I think that's in the list somewhere in that collection of examples. But I did, before we ran out of time, show you one that had only one. Also, if you do the this one that I'm about to show you, it doesn't have any spectator ions at all. Let me show you this one. How about this? Both of them are weak electrolytes. It's ammonium hydroxide, for right now, is the only weak base you will see. Ammonium hydroxide. And if it is an hydroxide from a transition metal, something off of the transition, it's a salt. You read that as a salt. So the only strong hydroxide forms a group 1, group 2 bases. And those are the strong bases. Group 1 hydroxides, group 2 hydroxides. Strong bases. Write that down 400 times. No, just kidding. Group 1 would be the lithium, sodium, potassium, rubidium, cesium, francium. Then you go over to the magnesium, calcium, and so forth, like that. And that's a 1-to-2 ratio between hydroxide and the metal in group 2. But if those are there, you classify it as strong bases, and they ionize 100%. So as you go through. But when you look at these two, this is ammonium hydroxide. It is a weak base, and this one is a weak acid. And you can still do the acid-base exchange between AXBY, and this will go to an ammonium acetate. See? Like that, because you're taking the ammonium and hooking it up with the acetate, and then that stays aqueous plus H2O as a liquid. That's the H and OH hookup. And when you write this out as an ionic equation, notice everything in here, well, this is a salt, so you have to ionize it 100%. Okay? But it's not a driving force. And I'll show you, it has to have something matching it on the left side to be a spectator ion. So when I write the ionic equation, I wind up with the ammonium ion and the acetate ion, because there's salt, because that compound's a salt, and then I put H2O as a liquid. But when I look at the ions against the reactant side, there are no matching formulas. And so this has no spec ions. Here's an example. Now, the last class of metathesis reaction is driven by what we call gas decomposition reactions. Right down here. And I give you a metathesis reaction over here to show you what essentially is happening. What happens, like in the CO2 as a driving force, it generates water also, and that's a weak electrolyte, but the gas is what is considered and defined as the driving force, not the weak electrolyte as in acid or base. Here you notice that a weak acid is generated in every case except the H2S, and that in itself is a volatile gas, and it comes out of the reaction. It smells like rotten eggs. Anyway, so you have the metathesis, but if you see this compound, or you see the nitrous, that's NO2 acid, or if you see the sulfurous acid, then you have one more step in your equation form, and those are written over here. What does carbonic acid is what it is. What does it go to? It goes to CO2 and water. So in gas decompositions, you have really to write your metathesis reaction, and it will generate a weak electrolyte, but you have to substitute for the weak electrolyte as a driving force the CO2 or the gas phase in water in every case in here. For example, and I'm showing the calcium carbonate, aqueous, plus the HCl aqueous, goes to, well, you've got the AXBY exchange, just like we've shown you. And so the hydrogen hooks up with the carbonate such that the sum of charges equals 0, just like we've been trying to teach you. So this is a calcium chloride aqueous, a salt, and it'll ionize 100%. And then there is the carbonic acid, H2CO3, as an aqueous acid. This is, in the strictest definition of driving force, is the driving force. But it's one of those compounds that you have to break down into CO2 gas and H2O as a liquid, and it's the H2O that's actually the final defined driving force in this process. So when you write this, you have one more step to write, and that's calcium carbonate plus 2HCl aqueous goes to the calcium chloride aqueous, because it's a salt, and then CO2, I'll come down here, plus CO2 gas plus H2O as a liquid. And that goes up and down. But at any rate, the CO2 is the driving force, and this would be your working equation if you were doing calculations or whatever. So in the same way with the others, if you have a nitrous acid, HNO2 generated, then it shows you in here what you have to break it down to. Now that has two nitrous oxide compounds, NO and NO2, plus the water that comes out of it. And then if you have the sulfurous acid, H2SO3 is a weak acid, and it breaks down to SO2 and water. So, it's just a matter of you recognizing the acid that breaks down. Now, the only one in there that doesn't break down but is considered a weak electrolyte driving force is H2S. You don't want you see that, stop. And that is your driving force, end of discussion. Now, the only base generated is, of course, that ammonium hydroxide, as you see down there at the bottom. And once you generate an ammonium hydroxide in the exchange reaction, get it all on one page. Yeah. So if you have something like ammonium chloride and sodium hydroxide, you can see the exchange, AXBY, gives you the salt and then that weak base. All right, now, as I said, ammonium hydroxide is going to be your weak base. Then you must substitute NH3 gas plus water liquid into the position for that compound. Okay.